And in this video, I will present my solution for the question 1 of the exam. The task is to write a program that's given 5 numbers and a target number n. Tries to build an expression using all 5 numbers exactly once, and the operators plus, subtraction, multiple, division, and exponentiations. So that's the expression evaluates to n. So for the problems overview, more formally, the problem is like input a set of 5 integers between 1 and 10 and a target number between 1 and 100. We must create an expression that uses each of 5 numbers exactly once, can use the operators plus, minus, subtraction, multiple division, and exponentiation, and evaluates exactly to n. For example, with the numbers like the set of number A7236 and the target number is 37. The valid solution is like 37. It means like it's equal to 7 multiplied by 2 plus 3 and plus A subtract by 6. So the assignment suggests is using recursive backtracking with brute force, and that is exactly the approach I implement in this notebook. So so my main function is called the solve target number function. Uh, the key ideas are represent the values as fractions. I use Python fractions type so that the division, uh, so that's the divisions is exact, no floating point routing. Comparison to the targets are reliable. Track both value and expression. For each partial results, I store the numeric value as a fraction and the corresponding expression as a string. Uh, for example, uh, the string like for like this, 7 um, multiplied by uh, 2 plus 3, something like this. And for the recursive backtracking, at each step, I pick 2 current variable A and B. Yeah, I gotta pick 2 variable A and B, and then remove them from the list and try to combine them with on the allow the with on allows operator like A plus B, A minus A subtract B, B subtract A multiply B, A divide B, and B divide A. If denominators are not zero, exponentiation in both orders with limit to keep is reasonable. So each combination produces a new values plus expression, and I recursively call backtracking with the smaller list. So for the base case, when there is only one value left, if it's equal um, to the target as a fraction, I will return its expression. And otherwise, I report no solution for that branch. So the recursive search explores all ways to parenthesize and combine the 5 numbers using the given operator. So to make the brute force practical, I add some important detail, memorization, catching, Many different operation orders can lead to the same multiset of value. I use canonical keys based on the short tuple of value and catch states that have already been explored with no success. Uh, if I reach the same multiset again, I immediately stop exploring that branch. Avoid division by zero before doing like A divide B. I check that like B is not zero, and likewise for B divide A. Limits exponentiation. Exponentiation can blow up very quickly. I only allow exponentiation when exponent is an integer with the small absolute value bound by parameter like max, like max exponentiation equal by 5. This will keep the number from becoming astronomically large while still allowing interesting solution. And the string expression with parentheses. Every time I combine two expressions, I wrap them in parentheses such as like this. I don't know how to say, but I'm gonna do like this. Or something like this. So this guarantees the final expression respect the intended order of the operation when evaluated. So for the course structure and sample executions, the notebook had two main code cells. The first defined by the solve target and the backtrack function. So the solve target gonna set up the initial list of the value expressions pairs using the original numbers. Then it calls backtrack on those values. Uh, the, and then the second cells runs the same execution. Uh, this one. So for each pairs of nums and targets, this one, it's called solve target function. And if the solution is found, it's print the expression and also evaluates with eval uh, to confirm that it matches the target. If no expressions exist under the constraints, it prints that no extract expression was found. The output demonstrates that the algorithm can correctly find solution when they exist and safely report when it cannot. Complexity and for this research, for this search space is large in theories because we are considering permutation of the numbers and combination of the operator. However, like with only this in video, the plus catching, pruning, and exponent limits, the program run effectively for the required input size. To conclude this solution, we use the recursive backtracking with the memoization, works with exact rationale, arithmetic, and fraction via fraction. handle all file operators, include exponentiation safely, and demonstrate correctness with these sample test cases. Thank you for watching my explanation of the target number solver for the question one.